You know, for most of automotive history, every single time an engine roared to life, it was secretly fighting with one hand tied behind its back. Yep, a tiny mechanical bottleneck that was choking its power, limiting its speed, and was just a constant source of failure. Engineers knew it was there, but for more than 50 years, they were basically stuck with it. Today, we're going to dive into the brilliant fix that changed absolutely everything.
So, what was this little tyrant holding our engines back? It wasn't the big stuff, not the pistons, not the crankshaft, not even the carburetor. No, it was a simple mechanical switch working under insane pressure that literally defined the absolute performance limit of what an engine could do.
Okay, so the source of all this trouble, it lies in the classic Kettering ignition system. This was the standard for decades, and the villain of our story is its most critical part, the mechanical breaker points. Their job sounded simple enough, just open and close a circuit. But oh man, the way they had to do it was just brutal.
Now what's really wild is just how many ways these little points could and would fail. I mean, think about it. They had to switch a high current circuit thousands of times a minute. Every time they opened, this created a powerful electrical arc that literally vaporized the metal on the contacts, causing pitting. At the same time, there was this little plastic block, the rubbing block, that would wear down on the distributor cam, physically changing the engine's timing. And at high RPMs, forget about it. The points just couldn't keep up. They'd physically bounce, causing misfires and a serious loss of power. It was never a matter of if it would fail, just a matter of when.
Just imagine you're in an endurance race, right? Like Trans Am or NASCAR. You're running an engine at its absolute limit for hours on end. This wasn't just some small inconvenience. This was often the deciding factor between winning the race and suffering a catastrophic failure. The breaker points were, without a doubt, the Achilles heel of every single performance engine.
So, how do you fix it? Well, the solution, and this is the really cool part, didn't come from better mechanics or stronger metals or anything like that. It came from the brand new world of electronics. It was a completely different way of thinking about how to build a switch.
And here it is. Meet the hero of our story, the transistor. It's what we call a solid-state switch. And that means no moving parts to wear out, no contacts to bounce, and absolutely no arc to burn away precious metal. It can switch electrical power on and off at incredible speeds, way faster than any mechanical device could ever dream of. So the big question was, how could you use this incredible new device to fix the old system?
And this is just genius. This shows the brilliance of the new design. You see, you don't actually get rid of the points entirely. Instead, you give them a new job. They no longer have to be the heavy lifter, the muscle, switching the full, powerful current of the ignition coil. Nope, the transistor takes over that brutal task. The points get demoted. They become a simple messenger, just sending a tiny, low-current signal to the transistor, telling it when to switch.
This clever new arrangement was called a contact-transistor ignition system, or TCI for short. And it's really a hybrid, blending the old, reliable mechanical timing of the points with the new solid-state power of the transistor, the best of both worlds.
So how does this dance actually work? It's basically a two-step process. First, you have the saturation phase. The breaker points close. This sends a tiny little electrical signal to what's called the base of the transistor. That signal is like a key in a lock. It turns the transistor fully on, and that opens the floodgates, allowing a huge current to rush into the ignition coil, building up a powerful magnetic field. Then comes the cutoff. The points snap open, and that tiny signal stops. Instantly, and I mean we're talking microseconds here, the transistor slams those floodgates shut. That sudden stop collapses the magnetic field, which in turn creates a massive voltage spike in the coil's secondary winding. And that, right there, is your spark.
Now, the numbers here are what really tell the story. The points, our old, worn-out component, are now only handling a tiny signal current of less than half an amp. It's barely a whisper. Meanwhile, the transistor is effortlessly switching the full 8+ amps of the main current. This separation of duties is what makes the whole system so incredibly reliable. The points just aren't in the line of fire anymore.
Of course, this all sounds fantastic in theory, right? But engineers, they need proof. They need cold, hard data. So they took this new hybrid system into the lab to see if the numbers really backed up the concept. And we're not talking about some backyard experiment here. They were using dedicated, professional test rigs like this EMA4 device to precisely measure and compare every single aspect of the ignition system's performance under controlled, repeatable conditions. The goal was simple. Put the old Kettering system in one corner and the new contact transistor system in the other. A head-to-head showdown. No guesswork, no opinions. Just cold, hard data on which one actually performed better.
And here's the verdict. Just look at these numbers. They speak for themselves. The primary current that the TCI system could handle was more than double the old system. Now, because spark energy is related to the square of the current, this isn't just a little better, it's a massive leap forward. And that leads directly to the next line, secondary voltage. The power of the actual spark doubled, from around 20,000 to 40,000 volts. But the real knockout punch? Point lifespan. It went from needing constant adjustment to lasting over 50,000 miles. The verdict was crystal clear.
So what did this victory in the lab actually mean out on the road? For real drivers? Well, it was nothing short of a revolution in how engines performed.
This wasn't just some small, marginal improvement. The secondary voltage could now hit peaks of 45,000 volts. That created a spark that was hotter, lasted longer, and was just vastly more powerful than anything a purely mechanical system could ever hope to produce.
And that powerful spark translated directly into real-world benefits any driver could feel. You know, easier starts on cold mornings, a smoother, more stable engine when you're just sitting at a stoplight, no more sputtering or misfires when you push the engine to high RPMs, and of course, a huge reduction in maintenance. But maybe most importantly, this hotter spark could reliably ignite leaner fuel mixtures, which was really the first big step toward better fuel economy and cleaner emissions.
When you really look back on it, the TCI system was so much more than just a clever fix. It was the essential evolutionary step. It was the missing link between the purely mechanical engines of the past and the fully electronic, computer-controlled power plants that we all have today. That basic idea of using a low-current signal to trigger a solid-state switch is the direct ancestor of every modern ignition system on the road.
So the transistor had solved the 50-year-old problem of that high-power switch. It was a true game changer. But the trigger, well, it was still a mechanical set of points rubbing on a cam. The system was reliable now, sure, but the next logical question was obvious. What happens when you replace that mechanical messenger with an electronic one? Well, that's a story for another explainer.